It's my pleasure today to introduce Kade Skelton. And Kade did her undergraduate degree at the University of Western Australia, and then she came to Darwin and did honors under the supervision of Hamish. And then I convinced her that geckos were a lot like crocodiles and that she should do a project on geckos, and she did. And she's going to talk to us today about some of her results.
All right, thank you, Keith. So yeah, hello everyone, my name's Kade Skelton, and as Keith said, today I'll be presenting my PhD project, which investigated the hydric and thermal physiological qualities of our North Australian dtellas. So dtellas are native lizards that belong to the genus of Geckos, and they're quite easily recognised by those nice large round, try and get the mouse here, large round toe pads you can see in the image here. As a genus, they are quite widespread in that you can find a member of the Geckos genus pretty much anywhere throughout the mainland of Australia. And these are quite an exciting group of species to study because many species have only been recently described in the scientific literature. And you might find that quite surprising, given they are so widespread throughout Australia that we're only discovering species as recent as the past few years. But one of the reasons for this is, if you look at the screen now, you're looking at 3 distinct species of dtella, and some of these species live in the same location and share the same habitat. So as you can see, they can be quite difficult to distinguish from their physical characteristics. So difficult, in fact, that for some species, you have to count the scales on their chin to determine species, or count the ridges on their toes to distinguish species. And even then, we were still largely relying on genetic samples in order to confirm, or in many cases, correct our field identifications. So as you can see, even though they are quite widespread, they are cryptic species in many cases, in the sense that they do look physically similar and in many cases share similar habitat. So that opens up a lot of opportunities for research though, because given they do look so similar and they are found in similar locations, then what is it then that distinguishes one species from another? In other words, what is it that distinguishes this small spotted terrestrial rock-dwelling dtella species that lives in Litchfield from this small spotted terrestrial rock-dwelling dtella species that lives in Litchfield? And so my PhD took the approach of analysing these species' physiology. So physiology refers to the ways in which an animal functions, so the chemical processes of the animal or the metabolic functions of the animal. So for my PhD, I focused on the hydric, meaning to do with water, and the thermal, meaning to do with temperature, physiological traits of these species. And these 2 traits are particularly important because the dtellas as reptiles are ectotherms, meaning that their body temperatures are highly reliant on their environmental temperatures to regulate their own body temperatures. And also, despite being recognised as very terrestrial and very well adapted to terrestrial habitats, reptiles are still particularly susceptible to water loss. So most of the water that these reptiles lose, that is not lost through excretory processes, so that's not lost through feces, is lost through passive evaporative water processes through their skin. So even though they are well adapted to terrestrial environments, they still do face many challenges in maintaining a hydric and thermal state, or in other words, they face many challenges in avoiding dehydration and ensuring that their bodies are kept at nice warm temperatures. So for my PhD, referring to the hydric physiology, I measured evaporative water loss rates. So evaporative water loss refers to the water that is lost passively through the skin. So here we have our dtella. It is consuming water, either by eating food which contains water or just drinking straight water. It is losing that water through excretion, through its feces, but it's also continuously losing water through its skin membrane through this process of evaporative water loss. And this is a continuous process, and it's measured as a rate of milligrams of water lost per minute. Now, this rate can change, and in particular, the rate can be increased by factors such as warm temperatures, low humidity, and high airflow. And many of these factors, you might notice, are associated with arid regions. So arid regions are characterized by low humidity. So for that reason, we might expect a difference in the evaporative water loss rates of dtellas from mesic versus dtellas from arid regions. So here we have our dtella in a mesic region. Mesic regions are characterized by having a humid environment, which means that this dtella is under low hydration stress. Yes, it's losing water to its environment, it needs to keep an eye on it, but there's not a lot of stress or a lot of pressure on maintaining a hydric state in this environment. So we would expect this mesic dtella to display typical evaporative water loss rates. Conversely, here we have a dtella in an arid region. Arid zones are characterized by having very dry environments. And as we mentioned, dry air can increase the rates of water loss. So this dtella is currently under high hydration stress. And if something doesn't change, it's at risk of dehydration. So what we expect is that the dtella from the arid region will be able to change and reduce its evaporative water loss rates in order to persist in this arid environment. So we would expect it to physiologically adapt to the arid climate, reduce its evaporative water loss rate, therefore reducing the amount of water it's passively losing to its environment in this scenario. Now, as for how we measure evaporative water loss, here's a very simplistic structure of the experiment setup. So first we take a baseline reading. And to do that, we pump dry air through an empty chamber. And as that dry air passes through the chamber and out the other end, we measure the humidity of the air. Now, obviously, we expect the air to come out pretty much just as dry as when it went in. Then we take a second reading by placing a single dtella in that chamber, and we repeat the experiment. We pass dry air through the chamber. That dry air will pass over the dtella's body. It will collect the moisture from the dtella's body that it's giving off through this evaporative process, and it will pass out the chamber. And again, we measure the humidity of the output air. And what we expect here, of course, is that that output air will be higher in humidity than what we get from the baseline reading because it contains the moisture from that dtella. So we take the difference between the output air from the baseline reading and the output air from the dtella reading, and that gives us a final measurement which can be used to calculate the evaporative water loss rate for that dtella. So that's quite a simplistic overview of that experiment design. What it looks like in the field is a bit more chaotic. We had 5 systems running simultaneously. You can see lots of components, lots of cords. The dtellas are contained in that grey incubator there so that they are maintained at a fairly stable and controlled temperature. And you can see there's lots of components going around here. This is the prototype setup before we got the laptop involved, but even then it wasn't much less chaotic. So that's what that looked like when we were measuring dtellas in the field. So that brings us to the thermal physiology of these species, which I measured by measuring their preferred temperatures. So preferred temperatures are a really important factor of thermal physiology, and that's because they represent the ideal body temperature. So when if other factors such as predators or risk of exposure are removed from the dtella's environment, so this was performed in a controlled environment where those influencing factors were removed, the resulting preferred temperatures represent the optimal metabolic function of these animals. So the temperature that their bodies function most efficiently and most effectively, and they don't have to have a trade-off scenario where they have to sacrifice their preferred temperature in order to escape predators. That's all eliminated. So in this controlled system, we have a terrarium and we have an artificial crevice here. So the reason we put a crevice in there is to mimic their natural habitat in the wild, again, to replicate natural behaviors and make sure that gecko is not under stress from being exposed. So we have an artificial crevice, and that artificial crevice has a thermal gradient from 20 degrees at one end to 40 degrees Celsius at the other. And this is maintained by placing a heat globe at one end of the tank. And this tank is contained within a controlled temperature room. So we're able to reduce the temperature of the overall environment down nice and low so we can get that thermal gradient. And that dtella is placed within that terrarium and it's able to move around and explore its environment as it wishes. And eventually it will pick a spot and settle down and select for a temperature where it feels most happy. So to extract the preferred temperatures from that setup, I used a thermal imaging camera, which produces these awesome rainbow dtellas we have up here. So one photo was taken of each dtella every hour to produce a total of 12 readings. Now, I took the median 6 readings from those 12 readings. That is standard procedure for this sort of analysis because it ensures that we capture only thermoregulatory behavior. So we only capture those temperatures where we can be sure that that dtella is choosing to select that temperature because it's truly the preferred temperature of that animal at that time. Now, if you look at these pictures, you can see there's little crosshairs on the lower abdomen of the dtella. That's where I selected the temperature from their body. As you can see, they get a bit cooler when you get to the extremities and they get much warmer at the center of their body. So that spot was selected because standard procedure is typically to take a cloacal sample, so to measure the temperature of the lizard or reptile internally through the cloaca. It's quite invasive. These are small animals. And we were taking samples and then putting them back in the experiment to measure them again. So a less invasive method was preferred here. So that's why we opted for the thermal imaging camera. So as for the actual species and sampling sites, I performed these experiments on 19 Gahara geckos, which were collected from a variety of West Australia and Northern Territory sites. I don't expect you to read the actual habitat structures of each of these sites. You can if you want to, but these are listed up in the map up above here. And the numbers in the circles represent the aridity of those sites. So number 1 is Litchfield. That is the least arid site. And it goes all the way down to number 11 here at Corundy Station, which is the most arid site. So we got a good variety of aridity amongst those sampling sites. Now, all 19 species were used in evaporative water loss experiments because we could measure that in the field. However, those thermal experiments, the ones with the rainbow dtellas, they only use Northern Territory species. And that's because of the logistics of capturing protected species in Western Australia, bringing them over the border, running them through experiments at CDU, and then going back over the border and releasing them back into their original habitat, because all of our dtellas did get released back into their original habitat after these experiments. So the first experiment was to measure evaporative water loss rates across all 19 species from West Australia and Northern Territory to see, do these species differ in their evaporative water loss rates? And what I found was that, yes, there was a significant difference across species in evaporative water loss rates. So up on the y-axis there, we have the mean evaporative water loss rates. And down below, I have each of my species listed in increasing mean evaporative water loss rate along the x-axis. So species do differ in their water loss rates, but the next step is to find where those species differences are. And so when I looked at which species were different, I found that actually the lowest evaporative water loss rate of Gahara giralulu was significantly different to 2 of the higher evaporative water loss rates of Gahara occidentalis and Gahara chimera. So the species circled in red was different to the species circled in blue, but other than that, there were no other species differences. There was a huge amount of overlap in water loss rates across our species. So technically, yes, there were species differences, but really when you looked into it, they were pretty minimal, and it seems to be driven by the more extreme ends of this water loss spectrum, if you will. So as I mentioned earlier, we did have an expectation of an association between evaporative water loss rates and aridity. Remember, we expected arid zone dtellas to compensate for their arid environments and reduce their water loss rates. So here we have, again, evaporative water loss rate on the y-axis up there. At the bottom, we have an aridity score. All you need to know is that it goes from least arid, up to the most arid towards me. So the higher the score, the more arid the sampling location. And you can ignore that blue line because what I found was that there was actually no significant association between evaporative water loss rates and aridity of the sampling sites. And that obviously contradicts with my initial expectations. There's a few potential explanations for this lack of association between these 2 variables. One of those is crevices. Dtellas spend a lot of their time in crevices. So I thought, well, maybe the broader climatic conditions are different across our sampling locations. But if geckos are spending a lot of their time in crevices, and those crevices create different conditions that are more similar across locations, maybe they're not actually exposed to these different broader climatic conditions. Maybe the habitats that they're spending most of their time in are actually quite similar, and that might explain why there's no difference across aridity. So when we were out in the field collecting these dtellas, I was also deploying loggers. So they're little eye button hydrochrons, which can measure the temperature and aridity of the environment. So I placed these eye buttons in crevices from select sample sites. And when I placed them in crevices, I also made sure to place one in the open air at the same location. It was in the shade, so it's shielded from the harsh sun. But what this allowed for was a comparison between inside crevice conditions and outside crevice conditions within the same location, but also across locations. So when we finally extracted and analysed that data, I produced this fun wonky graph, which I'm happy to explain after the talk. But ultimately, the main findings I found from that eye button data was that crevice conditions were actually different across sites. And also, crevice conditions did not differ to the outside conditions within locations. So that was surprising, and kind of my expectation that crevice conditions would be similar across locations kind of came to an end there. So to summarize the species and location comparisons across evaporative water loss, I found minimal differences between species, and neither broad-scale climate nor microhabitat conditions affected evaporative water loss rates. And again, there's a few more other explanations that could explain these results. One is that the dtellas are nocturnal. Being active at night means that they're not exposed to the extremes of temperature and aridity during the day, so they're not faced with the same pressures as diurnal or day active reptile might be. Or there may be some other reason going on that means that these dtellas do not need to specialize to their local climate, and we'll get to that a bit later in the seminar. So that brings us to our thermal preferences. So again, a species comparison in thermal preferences. Just a reminder, this is only considering Northern Territory species, so our list is a bit smaller on our graph here. But again, we have mean selected temperatures on the y-axis and then our species listed on the x-axis in order of increasing mean selected temperature. So what I found was that species did differ in the temperatures that they selected for in their preferred temperatures. And the two key findings from this is that Geckos showed especially low preferred temperatures. It had a mean preferred temperature of less than 30 degrees, which was unique amongst these other species. And also it was significantly different in its preferred temperatures compared to all other species. So something's going on with Geckos where it's selecting for particularly low temperatures. The other finding was that these three species that showed the highest preferred temperatures, they were all the only species that were sampled from Kade Station. And they're selecting for the highest mean temperatures there. So that led me to believe that perhaps there was an association between preferred temperatures and location. So I compared preferred temperatures across location just to confirm this. So just a reminder, these are our 3 Northern Territory sites. So you can see how they differ in their aridity there. And I found that preferred temperatures did differ across locations. Kade Station had significantly higher preferred temperatures compared to Kimmin Springs and compared to Litchfield. But Kimmin Springs and Litchfield did not differ in the preferred temperatures that were extracted from their species there. Kade Station had such high mean preferred temperatures that their mean was 33.6 compared to a mean of 30.9 and 31.4 compared to Kimmin Springs and Litchfield, respectively. And there's a few reasons for this, and that comes down to Kade Station's habitat and climate. So Kade Station species are relatively exposed to really strong thermal fluctuations. So as you can see, Kade Station is a lot more inland than the other 2 sites, and it's also the most arid site that we have in our samples. So Kade Station experiences very hot and very dry conditions during the day. But at night, those temperatures drop quite significantly, so they get very cold at night. So there's a really strong daily thermal fluctuations there. Kade Station is also characterized in terms of the habitat available to geckos, characterized by very small ground rocks, which have very shallow crevices. So there's not much shelter from these hot and dry conditions during the day, but these small rocks can heat up really quick and they can hold that heat during the night when the air temperatures are very cold. So it's possible that these species may be selecting for higher temperatures because they're seeking those warm habitats within the crevices at night when the air temperatures are cold. But that's just a bit of speculation because unfortunately we didn't measure the crevice conditions at Kade Station. So it's a possibility that there's a relationship there between microhabitat and the dynamic that has with the external habitat. But that's just a potential explanation for that pattern. Now, what about Geckos, that gecko that showed really low preferred temperatures? So Geckos was sampled in this case just slightly out of Kimmin Springs, a quite a unique habitat in that it was this limestone outcrop which formed these really tall hills and had very deep crevices, very deep limestone fissures. Some of these crevices were more than 10 meters deep, and that's unique compared to the other sampling sites from Litchfield and Kimmin Springs. Now, I did measure the crevices at this location, and I found that the crevices were not different in their temperature and their humidity compared to outside the crevices here. However, the really deep crevices that are like 10 meters deep, they were severely underrepresented in that study. So most of the crevices that I put loggers in were very shallow. Most of the loggers only went less than 1 meter deep in the crevices. So the shallow crevices didn't show a difference to the external temperatures, but those really deep crevices may be harboring an environment that is significantly different to the external environment. And I did have one logger that was placed deep in a crevice. So I had one eye button that was placed 5 meters deep in a crevice that was at least 10 meters deep in total. And what I found was that in that really deep crevice, it had lower minimum temperatures, lower mean temperatures, lower maximum temperatures, and more stable temperature readings compared to both the shallow crevices at the same site and the external conditions at that same site. So this shows that there's potentially this really deep crevice habitat that maintains cool and stable conditions that's available uniquely to this species. And remember that these dtellas are nocturnal as well. So during the night, they're coming out to nice and cool temperatures, and during the day, they're retreating to these very cool and stable conditions. So there's potential that this microhabitat might be allowing for these dtellas to adapt to cool conditions because they're the conditions that they're exposed to most of the time. So again, that's just a potential explanation for what's going on here, but has not been confirmed. So to summarize my thermal preferences section of this study, we found that local conditions can potentially influence thermal preference, and it seems that access to reliable microhabitats is important in influencing preferred temperatures. All right, so this little dtella here, this is a Gahara lepistula. He's in there to remind me to take a breather and take a break because I tend to talk in continuous run-on sentences. So if you just give me a minute, I'm just gonna have a drink and take a breath to make sure that I don't rush through the rest of this presentation, but you can watch this cute little guy run in circles for a little bit. You can see those toe pads there too. Alrighty, so I'll try and slow myself down. So to summarize everything we've covered so far in terms of the species and location comparisons, we find that the dtellas are not specializing in their evaporative water loss rates, and contrast between microhabitat and broader climate may influence thermal preferences, that relationship within locations. So that brings me to the next portion of my PhD project, which looks at physiological plasticity. So plasticity refers to the capacity to change or adapt. So here we're talking about the capacity for hydric or thermal physiological traits to shift in response to changed environmental conditions. So that's the question I'm asking here. Can dtellas change their hydric or thermal physiology in response to changed environmental conditions? And there were two approaches to this question. The first was to take field measurements just as before, but this time taking those field measurements in wet, early dry, and dry season. So we have 3 distinct seasonal categories. And the second approach is acclimation treatments. So dtellas were taken into the lab and they were kept in controlled conditions for a month. And then the measurements were taken again after they were acclimated to either of these acclimation treatments. So for evaporative water loss experiments, we acclimated dtellas to either humid or dry conditions to see if that acclimation can impact the resulting evaporative water loss rates. And for thermal preferences, dtellas were acclimated to either warm or cool conditions to see if they will change their thermal preferences in response to those conditions they've been exposed to. Now, again, for this experiment, we're looking at Northern Territory species only because it does involve a lot of lab work and holding on to animals for a long time, plus frequently repeated field measurements. As much as I'd love to go to the Kimberley in wet, fairly dry and dry season, it's not feasible. So here we have the evaporative water loss rates of our Northern Territory dtella species and how they measure across each season. So on the y-axis here, again, we have our evaporative water loss. We're familiar with that now. On the x-axis, we have wet, early dry, and dry season. So the different colored dots represent what each of the individual species are doing. But if you just want to look at those white boxes, because it can be hard to distinguish those little colors up here, those white boxes show you the general trend of what's going on here. And as you can see, it's probably quite obvious to most of you right away, there is a strong seasonal response in evaporative water loss rates. In fact, evaporative water loss rates were reduced by up to 78% between wet season to dry season. And not only did they reduce in the rate of evaporative water loss, but also the variability in evaporative water loss rates was reduced up to 98%. So what that shows us is that these species are reducing their evaporative water loss rates quite strongly in response to seasonal shifts. But not only are they reducing their evaporative water loss rate, they're all converging to similarly minimal evaporative water loss rates. There is also a significant difference in the water loss rates between wet season and early dry. So early dry was around the May, June area, time of year. So what that shows us is that there's a rapid onset of this seasonal response. So it didn't take all of dry season for these dtellas to eventually change their physiology. They were able to shift that physiology quite quickly in response to that early seasonal shift. However, there was no difference between early dry and dry season evaporative water loss rate. So that difference was not significant, but water loss rates were lower in the dry season in most cases than they were in early dry. So that shows us that they're changing really quickly in response to seasonal change, but they are taking a while to reach that minimal evaporative water loss rate. What this also shows us is that there's potentially a cost to maintaining this low evaporative water loss rate, because they are shifting specifically to this low rate during the dry season when obviously it's dry, there's a low humidity in the environment. So they're responding to that increased pressure, increased stress on their hydric state. But when it comes to wet season, they're kind of letting their water loss rates go. They're not as strict on reducing those rates there. So after measuring those water loss rates in the field, remember we have these acclimation experiments. So we measured them in the field and then collected them, took them to the lab and split them into 2 treatment groups. One was humid at 80% relative humidity, and one was kept at dry conditions at 20% relative humidity. And they were kept at those conditions for a month to see, does long-term or month-long long-term exposure to these specific environmental conditions impact their evaporative water loss rates. And unfortunately, I could not find that same strong response that we saw in the seasonal data in the acclimation data. So most species did have lower water loss rates after being acclimated to the dry treatment rather than compared to those acclimated to the humid treatment. However, this was only a significant difference in 3 of the 10 species. So they were trending towards the same pattern, but it wasn't really that significant in most cases. And a potential explanation for this is that captive conditions were not truly reflective of field seasonal conditions. So what we did was, when we had dtellas in captivity, we were providing them with fresh water every day and we were feeding them regularly. And that might have impacted our dry acclimation conditions as those dtellas were receiving water every day. So they weren't under the same level of hydric stress as they may be in the field. And to support this, I compared the humid acclimation water loss rates to the field wet season water loss rates and found that they were not different. So they were having similar water loss rates under those conditions. But I compared the dry acclimation water loss rates to the field dry season water loss rates and found that those water loss rates were significantly different. So there's a potential there that, yes, those captive conditions in dry acclimation conditions were not stressful enough, if you will, potentially to reflect what's happening in the field. But as I said, that was for ethical purposes to make sure our dtellas were well looked after. So there is a potential, given that it was trending in that direction, that seasonal evaporative water loss rates could be replicated in acclimation studies if we didn't feed them so much. As for thermal preferences, I found no difference between wet and dry season in thermal preferences of our studied dtellas. That tells us that thermal physiology doesn't seem to be shifting across seasons in these dtellas, which means that they're probably maintaining their same preferred body temperature through behavioural changes, through shifts in the way that they use their habitat. And just so we're aware, this graph only displays Litchfield species. So only Litchfield species were measured here for the field seasonal thermal preferences. So they're not showing much of a change throughout the year in their preferred temperatures. But then we come to the acclimation experiment. So in this case, dtellas were split into 2 groups. Warm treatment was kept at 32 degrees for a month and cool treatment was kept at 22 degrees for a month. And then their thermal preferences were measured again after acclimation. Now this experiment included Litchfield species, but it also included Kidman Springs and Corundy Station species. So we had a larger sample size for these acclimation studies. And what I found was that most species didn't differ in their thermal preference after acclimation to either conditions, except for the 3 species from Corundy Station. and they show a case of reverse acclimation. So when they are acclimated to warm conditions, those 32-degree conditions, they come out and they present a thermal preference that is 4 degrees cooler than those that are in the cool treatment. So rather than increasing their thermal preference to match their increased environmental temperatures, they're actually showing an opposite effect. They're creating greater contrast between their thermal preference and their environmental temperatures. All right, so to summarize the physiological plasticity portion of this study, we find that there is a strong seasonal response in evaporative water loss. This could not be replicated in acclimation studies, but there is potential that it could be. Thermal preference seems to be fixed and rather behaviorally regulated rather than physiologically regulated. And corundistation species are showing a case of reverse acclimation. And remember, corundistation is characterized by strong thermal fluctuations, both daily but also seasonally as well, and also thermal extremes. Now, I say thermal extremes, but that's relative to Kidman Springs and Litchfield. That's not like it's getting below freezing on a regular occasion in corundistation, but relative to what we experience closer to the top end, corundistation is experiencing more extreme hot and more extreme cold temperatures. So it's possible that these dtellas at corundistation are selecting for a contrasting temperature in order to reach their true preferred temperatures faster and maintain that for longer. So it's just a more efficient way of reaching stable body temperatures when they're faced with these extreme temperature fluctuations. All right, so now we've reached the final experimental component of my PhD, and that's looking at physiological priorities. So in other words, is maintenance of hydric state or thermal state more important? Because maintaining either of these physiological characteristics, it's often a conflicting aim. So in the wild or in nature, if you're finding a humid environment, chances are human environments are often quite cool. So it's good for your hydric state, but for your thermal state, you're going to be at a loss. You're not going to be as warm as you want to be. Whereas if you want to find a nice warm spot, chances are that place is going to be very dry. So it's great for your temperature, but it's going to put you at a greater risk of water loss. So they can be conflicting goals, especially in the dynamic natural environment. So that means that one trait is going to have to be prioritized over another. There's going to be a trade-off scenario here. And so the purpose of these studies is to test which trait is prioritized, at least in the short term, and when do these priorities switch. When we increase the stress on one physiological trait, does the preference for maintaining either of those traits switch? So ultimately, it's asking the question of which physiological trait is at greatest risk in the short term. So to test the preference of maintaining hydric or thermal state, we have a terrarium and we have two crevices. We have a humid crevice and a dry crevice, and the dtella is free to select from either crevice. Now, the dry crevice is always kept at 32 degrees. So this crevice is always dry and always warm. The humid crevice, however, can be kept at 22, 27, or 32 degrees. And that temperature will match the temperature of the overall terrarium. So there's 3 treatments here in which the dry crevice always remains dry and warm. So that's what these 3 treatments look like. At the 32-degree treatment, there is no difference in temperature across the scene. The only difference between those crevices is one is dry and one is humid. At the 27-degree treatment, there's a 5-degree difference between the dry crevice and the rest of the environment. And of course, 22-degree treatment, there's a 10-degree difference. So we're basically increasing the level of stress on their thermal state to assess if that's going to cause a change in preference for either of these crevices. So this is what that looks like in real life. So this is a video. So basically we take a video of the setup, and that video is comprised of photos that are taken at 10-second intervals. And so at this point in the presentation, I'd like to thank Kimberly Day for being an excellent research assistant for this project. I was too busy fighting with R to get my code to work and analyze some data. She sat in a dark room going through hundreds of these videos that were very long, recording the exact time that a dtella would enter or exit either crevice. And when you got a dtella like Gemina 190 here, that's quite a task. So as I said, these videos were comprised of a photo taken every 10 seconds, and we can record the time that the dtella spends in either crevice, and also the number of times the dtella visits either crevice and stuff like that. So that's what that looks like in practice. I'll let him finish running around. It won't take much longer. All right, there we go. All right, so the first lot of data that I extracted from those videos was the crevice use. So how much time did those dtellas spend in crevices? It doesn't matter if it's a humid crevice or a dry crevice, just how much time are they spending in crevices? And this is across the 3 treatments. So here we have the mean proportion of time spent in a crevice, and it ranges from 0 to 1. So this is proportional time. So 0 means that they are spending 0% of their time in a crevice. They are out and about the whole experiment. Value of 1 means that they are spending 100% of their time in a crevice. They are under that crevice the whole time they're in the experiment. And here we have a 32-degree treatment. Remember, temperatures are equal across the scene, a 27-degree treatment, and a 22-degree treatment. So what you can see quite readily is that there is a significant increase in the use of crevices when those environmental temperatures drop. All species actually spent at least 90% of their time under a crevice in the 22-degree treatment. So we can see that when it starts getting a little cold, they all retreat into crevices. However, as I said, we haven't distinguished which crevice they are using. So the next step is to determine if there is a preference for either crevice. So this first step is important to clarify, because this next step looks at the proportion of time spent in the humid crevice relative to the dry crevice. So this considers only the amount of time that they are under a crevice. How much of that time are they spending in humid compared to dry? So again, we have our mean proportion time on the y-axis. Again, that's from a value of 0 or 0% to 1 or 100% of their time in the humid crevice, and our 32, 27, and 22-degree treatment. And as you can see, there is a significant decrease in the selection for the humid crevice as temperatures drop. Or in other words, there is a significant increase in the selection for the warm, dry crevice when temperatures in the scene decline. All species spent less than 5% of their time under crevices under the humid crevice in the 27-degree treatment. So it only took a 5-degree drop in their environmental temperatures to trigger this strong response. Or in other words, in the 27-degree treatment, all species spent at least 95% of their time in the dry and warm crevice. So what we're seeing is that there is a huge preference for that warm crevice. They want to stay warm, even at the risk of their hydric state. They are prioritizing staying warm. Now, on that note, this part of the experiment is of particular interest. So at the 32-degree treatment, temperatures are equal throughout the scene. So the only difference between the 2 crevices is that one is humid and one is dry. So I wanted to see, okay, when all other conditions are equal, do dtellas prefer the humid crevice or the dry crevice, or is there no preference? So what I expected was that given all other conditions were equal, dtellas would select for the humid crevice. They're going to be warm either way. So if they can also maintain an ideal hydric state while they're at it, reduce their stress or risk of dehydration, surely they would select for the humid crevice if they have the opportunity. However, I found a very mixed trend. So here we have our species and our mean proportion of time spent in the humid crevice specifically. And again, this is just the 32-degree treatment. And we find that our species are kind of all over the place. They're all doing different things. There's not a universal trend or selection here. So they're all tending towards different amounts of time spent in the humid crevice. But the next step was then to say, okay, are any of these species actively selecting for one over the other? Are they just happening to spend more time in one or the other? Or is there an active preference for one of these crevices? And to do that, I tested these values against a value of 0.5. So again, this is proportional time ranging from 0 to 1. So 0.5 is a value which represents a dtella spending 50% of its time in one crevice and 50% of its time in the other crevice. So it's spending perfectly equal amount of time in either crevice. So we can conclude that that is truly no preference for either crevice type. So if their results are different to a value of 0.5, then we can say with some statistical confidence that they are actively choosing and preferring one of these crevices. So I performed that test for each of our species. And what I found was that 2 species actively preferred the dry crevice, 2 species actively preferred the humid crevice, and the rest of the species didn't know what they were doing. So quite a bit of mixed results in that respect. So to summarize that portion of our experiment, I found that there was a strong selection for warm environments in dtellas. It seems that maintaining body temperature is the main priority, even at the risk of increased water loss and increased dehydration. And it seems that reducing stresses on hydric state is not that important. As I said, I expected them to select for human environments, given all other conditions were equal, but there wasn't a universal trend to do that. It was all a bit mixed. Different species were doing different things. So that finishes the experiment part of my PhD. So now we can summarize all the findings completely. So I found that evaporative water loss rates did not differ across species or climate, but they did show a very strong seasonal response. Thermal preferences seemed fixed and they were maintained behaviourally, and we can confirm this because in these prioritisation experiments, we can see that maintaining thermal state, at least in the short term, seems far more important than maintaining a stable hydric state. So from these findings, I can conclude that for evaporative water loss rates, physiological plasticity negates the need for physiological specialisation. So in other words, dtellas are flexible in their water loss rates. They don't need to reduce their water loss rates and fix at that low rate to cope with arid zones if they can remain flexible in their physiology and reduce it when needed and release that pressure on their evaporative water loss rates when it's not needed. And so this potentially explains the lack of differences across species and across aridity of locations. Again, they don't need to specialise for these climatic conditions because they can just shift and match whatever they're dealing with in the moment in their environment. As for thermal preferences, it seems that access to ideal or at least tolerable temperatures in their environment negates the need for physiological plasticity. As far as what we can see, they're not physiologically shifting their thermal preferences, and that's probably because they can access temperatures that are beneficial and allow for them to reach these thermal preferences. They don't need to shift physiologically because they can be maintained in the short term behaviourally. And we can see that that trait is prioritised, at least in the short term, because they will sacrifice their hydration state to maintain this thermal state in the long term, because they can maintain hydric state long term through these seasonal fluctuations, their physiological plasticity. But for thermal preferences, if they can maintain them behaviourally in the moment and they don't have to have any stress on that, then they will do so. There are a few considerations to keep in mind when interpreting these conclusions. The main one is that these species are from wet, dry, tropic sampling locations, which means there are huge differences in the humidity between wet and dry season, not so much in terms of temperature. Our temperature doesn't change heaps between wet and dry season, at least if you compare to other climatic regions. So, you're going to get a 32-degree day in wet season, you're going to get a 32-degree day in dry season. So there is a fluctuation in temperatures there, but not as strongly as humidity. So even in the arid climate, our Kade station, the most arid sampling site that we had in this study, even that still experiences high humidity in the wet season. So that kind of further explains why they'll be showing physiological plasticity and not fixing to a really low evaporative water loss rate, because even when it is the most arid and they are under the most stress, they're only under those circumstances for about half the year. Then the wet season comes along and they don't have to maintain that really low evaporative water loss rate. And as we mentioned, there's a potential cost to maintaining such low rates. So why endure that cost if it's only going to benefit you for half the year, if you can remain plastic and just match with what you're dealing with in the moment? Now, as I said, the seasonal changes in temperature in these environments are not as extreme as the changes in humidity. However, Kade station does have the most extreme seasonal temperature fluctuations, as we discussed, and it's also the only location where our species showed a shift in their preferred temperatures. So further investigation of these arid zones and the relation between thermal and hydric fluctuations throughout the season and how they relate to microhabitats will be a good future avenue for further physiological studies to see how these physiological traits relate to species, but also specifically relate to their environments. So that does conclude my presentation for today. So thank you all for coming along. I've actually run under time, so I must have spoken too fast, so I apologise. But I will be hanging around for questions. So if, just give me a moment to, again, slow myself down, and I'll be happy to answer any questions at a normal human pace. But thank you all for coming along. You can contact me at that email if you won't have any questions at a later time, but thank you. Oh, yeah. We've only got one, so we might have to. Oh yeah. Okay, you take that one. On the. Oh yeah. Okay, it's green. We'll see how it goes.
Oh, yeah, look, thanks, Kate. That was a great presentation.
Thank you.
So really, thanks for that. I've got a comment and then a question.
Yep.
And my comment starts off with you can tell that Unger and you share a common advisor for your physiological experiments, can't you? So for those don't know what that means, so Keith and I share a student who's done a lot of similar experiments in the context of responses to fire.
Okay.
And so my comment was that so the context of the firework for Unger's project was the expectation that because the effect of fire on most fauna is through habitat change, we would expect that those that are favoured by frequent burning, in other words, favoured by more open habitats, would have those predicted differences in evaporative water loss and thermal temperatures. And we found the results were it's very weak, a bit like you've had, very weak, some of the extremes, but mostly there was no difference amongst most of them. So I guess my comment is that plasticity, physiological plasticity you're talking about, confers resilience of these lizards to variation in fire regimes. Anyway, so that's
absolutely. So kind of broader conclusion is, they're flexible in their evaporative water loss. It doesn't seem to be a huge stress for them at this point, whereas thermal preference might be I think
even for thermal. Look, I can't. Remember.
That's a bit of
anyway. So it's got an interesting implication. In terms of responses to fire here. So my question was the relationship between evaporative water loss you showed and aridity. Can you go back to the slide?
Yes, I can.
I'm not quite sure that I'd be dismissing that entirely, because my looking at those data, let's have a look at that.
Nearly there. Yep.
Would suggest just looking at the data is that, there's no relationship up until 30, whatever it is, 2.
Yep.
But those dots near the 40, do stand out as very low variation. So everything there was low. And I'm just wondering if you compared those data with the rest, I suspect you'll get something statistically significant.
Yeah, so that's Corundy Station, and that's those just 3 species from Corundy Station. And as you probably noticed, they've made a fair feature throughout the presentation. I can identify them here. So they are on the lower end for the most part. So we have, this is one. Maybe we can use a texter.
Yeah, so I was thinking more to do with just not so much species specific, but just looking at that general relationship.
Okay, just Corundy
and the
versus
implications. So if you go back, so it's not even worrying about locations, and maybe it's, if you just look at that relationship, one conclude if there is a statistically significant difference between those N ones and the rest, the conclusion would be that there's nothing happening up until a point. But once you get extreme aridity, there is something.
I understand what you mean now. And that's kind of what other results are inferring to, in that once you start getting those, the arid location with the strong fluctuations across season, things start looking a bit different, because in terms of evaporative water loss, they are flexible, but the ones up here, we still got strong wet and dry conditions. But those seasonal differences aren't as strong. So absolutely, when you start getting to those extreme arid zones, and that's why they'd be interesting to look into further, even more arid than Corundy Station if possible, and see if that pattern continues, and if there's a point of aridity where they start shifting.
And so it might be worth thinking about just nuancing that conclusion you've got of no significant association, in the sense that maybe overall, if you did a statistical test, it doesn't. But if you focused on the extreme versus the rest, you might. And so that would nuance. It's not quite the conclusion.
That's a good point. Thank you. So it's that one at the end is definitely interesting things to research in that respect. Thank you. Anyone else want a question?
So I might just ask question. So would you want to comment on the sort of time scale? So you found differences with respect to water stress versus temperature stress or temperature exposure and exposure to desiccating or drying conditions.
Oh yeah, sorry, in terms of the prioritization.
Just in terms of time scale. In other words, you looked at how long.
Oh, okay.
So if an animal gets too cold or too hot, what's that danger in a short time, on one time scale, but what's the equivalent danger of being in really dry conditions
Long
on a
term.
time scale?
Yeah, okay. So I think I understand what you mean. So short term, or at least over the course of a few months, they seem to be able to persist, shift their physiology or in the case of thermal preference, find suitable environments. But it seems that they're going to have to bounce back to those high evaporative water loss rates at some time, because it is occurring a cost to some degree of reducing their water loss rates. So they can bounce back and forth seasonally, but if they were in a severely arid region, are you talking about like if they're dry for years and years and there's a drought, or like in the field? Or
you did some calculations to look
Yes,
at how long they could survive.
oh yeah, okay, sorry, yeah. Let me be specific with me. So I took the evaporative water loss rates from the dry season, so when they're under the most hydric stress, but they reduce their evaporative water loss rates pretty much, as far as we know, as much as they can. It could be a bit further. And using those rates, I calculated how long they could survive without water intake before they reach a vital limit of desiccation. And some of these species could last 2 weeks or more without any water intake before they reach the vital limit. So yeah, sorry, I understand what I'm thinking about 6 other things. So yeah, in the field, they could, if they reduce their evaporative water loss rates really low in response to really dry conditions, and they can persist without food or water intake for, some species it was more like a week, other species it was edging close to 3 weeks, a month. So it was a bit variable there. The capacity to reduce your water loss rates to the point where you can last that long without food or water intake indicates that, it's quite effective in maybe letting them persist through a short-term drought or lack of food availability in the deep of the dry season. Yeah. Does that answer what you're getting at? Yeah.
Yeah,
okay.
yeah. But then just in like contrast, if an animal gets above its critical thermal maximum,
in comparison,
minutes as opposed to weeks.
Yeah, so they can last weeks, nearly a month without water. But in terms of they can't sit in 40-degree heat for long before they're going to cark it, or 10 degrees before they're going to slow down too much. So so that's also why it's prioritized in those experiments as well. It's important that they maintain it short term. The risks are greater short term.
Any other questions?
I would just compliment you on your style.
Oh, thank you.
And you can make a wonderful lecture about that.
Oh, I appreciate it. Thank you. As long as I can remember to breathe, I think I'll be. Yeah, that's my rule. If it's as long as there's a picture up there and people are looking at the screen. But I appreciate it. Thank you.
Okay, well, let's thank Kade one last time.
Thank you. As I said, I hung around for a few minutes outside if you wanted to ask questions. Yeah, so just outside by the chairs, I believe, the picnic benches, there'll be drinks and snacks. So thanks.